There are phrases that are truly timeless and universal. For instance, love conquers all. Or to be or not to be, that is the question. And of course, heard about room temperature superconductors. They will revolutionize the world. Superconductors are like nuclear fusion. It's a technology that, when fully mastered, will change the world, but it is quite vague and always seems to be in the near future. Since the year 2000, over 12 research groups around the world have reported finding a room temperature superconductor. Some of these were incorrect or even falsified results, and the other part were actual room temperature superconductors, but they needed to operate at very high pressures to be practical. But that changed in July 2023 because a group of researchers from South Korea claimed to have found a superconductor at room temperature and pressure. That said, this result has not yet been peer-reviewed, and attempts to replicate the experiment have also not been thoroughly reviewed. There are scientists doing live streams of their attempts to replicate the paper and test the new superconductor, which I think is super cool. So, currently, at the date and time this video is being recorded, I cannot say if we have found a room temperature superconductor. If this is confirmed, we will definitely have a video about it, probably when they win the Nobel Prize in Physics that they deserve. But what I can do is explain to you what superconductors are, how they will change the world, and why we have a lot of work to do before they actually change the world.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
The year is 1911, and physicist Heike Kamerlingh Onnes is studying the properties of the metal mercury at low temperatures. In particular, the electrical resistivity of mercury at the temperatures of liquid helium, which is about -269 degrees Celsius, is very close to absolute zero. Electrical resistivity is the quantity that represents how materials resist electric currents passing through them. Materials with high resistivity are resistors. And converting electrical energy into heat, one of the main functions of resistors, powers electric showers. Low resistivity materials are electrical conductors. So, they transmit electrical energy efficiently, like the wires that connect your house to the power grid. And, that being said, even electrical conductors have a bit of resistivity, a bit of resistance, so they lose some of the electrical energy they transmit as heat in the process. Onnes and his experiment with mercury cooled with liquid helium. The first test, on April 8, 1911, shows the electrical resistivity of mercury at these temperatures is lower than could be measured. So he sets up a precise experiment, measuring small resistivities, and the electrical resistivity of mercury remains below what he can measure. At this point, he becomes convinced that he has found something special, and he called this special something superconductivity, which we today call superconductivity. Superconductivity is a state of matter like liquids, solids, and gases. When water is cooled to 0 Celsius, it freezes. When certain materials are cooled sufficiently, they enter the superconducting state and lose all resistance to the transmission of electrical currents. In other words, it becomes practically possible to move energy freely within the material, avoiding energy loss effects such as heat emission. Onnes even thought of an experiment to investigate if mercury at low temperatures had 0 electrical resistivity. For this, he created a simple electrical circuit with mercury, injected electric current, and measured how the current decreased over time. In a common conductor, the current would soon disappear due to dissipative effects, such as heat emission. But in superconducting mercury, the current remained alive even without a power source. There was no loss of electrical energy in the superconductor, it actually had 0 electrical resistance. This is very useful in theory. I'll discuss how to use this later in the video. Actually, experiments to measure the Earth's gravitational field precisely use superconductors in a very similar way. And one of these experiments maintained an electric current alive for 27 years inside a superconductor without addition of energy after the initial current was injected. In other words, there was absolutely no significant energy loss even 27 years later. Superconductors are basically magic, but magic that only works when cooled by liquid helium, which isn't exactly useful. And not only that, the physics behind it was quite elaborate. There are several models of how superconductivity arises in materials, but all of them are quite complicated and none are perfect. So much so that superconductivity is a field driven especially by experimental discoveries and effective models, which try to guide experiments rather than explain the fundamentals of superconductivity. Because of this, we will not go into the details of the microscopic theory of superconductors. The next major discovery about superconductors occurred in the 1930s, and it is about how superconductors interact with magnetic fields. The answer is that superconductors refuse to interact with magnetic fields. If you pass a magnetic field through a metal, it will become magnetized and gain magnetic properties in the presence of the field. Now, if you cool a metal to its superconducting temperature, the superconducting metal will expel the magnetic field from within itself. It will resist having any magnetic properties. And this expulsion is so intense that it can serve as a basis for magnetic levitation technologies, such as those maglev trains. Maglev trains are extremely high-speed trains that avoid touching the tracks by using magnetic levitation. They don't always use superconductors, but if superconductors at room temperatures became practical, it would be much simpler to make a maglev train. But before we talk about room temperature superconductors, we need an intermediate step. High-temperature superconductors were discovered in the 1980s and 1990s and gave hope that there might be superconductors at room temperature. But do not confuse high-temperature superconductors with room temperature superconductors. The difference between the two is still grotesque. High-temperature superconductors operate at liquid nitrogen temperatures, minus 200 degrees Celsius, which is 70 degrees warmer than usual superconductors. And this is extremely useful. It is much easier to obtain liquid nitrogen than liquid helium. That said, despite having a more manageable temperature, high-temperature superconductors are usually made of ceramic materials rather than metallic materials. This makes them impractical but not impossible, for example, to create long conductive wires with ceramic superconductors. Even so, these superconductors are certainly very useful, especially with high-power electromagnets. Electromagnets create magnetic fields using electric currents in a process called magnetic induction. The more intense the electric current, the stronger the magnetic field generated. But in a normal conductor, electric current also turns into heat. A powerful electric current can melt the conductor. Superconductors, on the other hand, do not have this problem. Superconductors do not dissipate electricity as heat, so they can sustain much higher electric currents and generate much more intense magnetic fields. This is the tech basis of magnetic resonance imaging, MRI devices used in hospitals every day. Superconductors already have practical applications saving lives. We already have a list of several high-temperature superconductors. The next step is to further increase the temperatures and finally find superconductors that work under ambient temperature and pressure conditions. And this is something investigated by numerous groups around the world, a discovery that would lead to a Nobel Prize and numerous technological improvements. But what exactly would change in the world if we found this perfect superconductor in the world? Obviously, nothing too significant would change. There aren't many new technologies that would come from superconductors, except perhaps for nuclear fusion and improvements in space travel. Nothing new. What would change is that it would be possible to make greatly improved versions of technologies we already use. The whole world would change with that. For example, with a superconducting wire, you could transmit enormous amounts of electricity with a single wire and without losses. This would make a country's power grid extremely more compact and resistant to natural disasters. Furthermore, energy transmission would be perfect, without losses, which could generate a global energy saving of 20% that is normally lost in dissipation. In other words, without building any new power plants, humanity could increase its energy usage by 20% using superconductors. Another interesting use is in microchips and digital circuits that do not heat up. If you're a gamer and want to play, I don't know, some League of Legends every night, you know that computers heat up when performing heavy computations. Not that League of Legends is heavy, but the example will do. This is due to the dissipation of electric current into heat. Microchips based on superconductors would not have this problem, which would allow more microchips to be placed nearby without worrying about how they would cool down and perform very high-frequency computing without generating absurd amounts of heat. And here is an unexpected example. In theory, it is possible to use magnetic fields generated by superconductors to cheaply separate materials with different magnetic properties. It would be possible to create a magnetic water filter that purifies in ways 100 times more efficient than modern technologies. And these are just some of the technologies that can be improved with superconductors: communication systems, motors and generators, particle detectors and accelerators, even nuclear fusion reactors. As a rule, if there is a robust electrical circuit or an intense magnetic field involved in the technology, we can improve it with superconductors. And that is why superconductors are so desired. They could provide the greatest upgrade in human capacity to use energy since the discovery of electricity. It would be practically our generation's version of the invention of the transistor, which enabled modern computing. But we can't get too excited yet about LK99, the supposed room temperature superconductor.
Science is a rigorous process, requiring a lot of research and testing before confirming if it is the first room temperature superconductor that humanity has ever created. What about you? Which application of superconductors in everyday life are you most excited about? Thank you very much and see you next time.